All right, so where we're headed next is we want to basically extend everything that we've done in 2 dimensions to 3 dimensions. And we've started doing that by looking at triple integrals, but there's another concept that we need to extend to 3 dimensions, which is the idea of a flux integral. So we're going to have to do this in stages, though. Remember, the idea here is if we have some vector field in space, right, so and we want to calculate the flux, well, you have to ask, the flux through what? I mean, in 3 dimensions, right, it doesn't really make sense to ask about the flux across a curve, because a curve doesn't really have an across, right? A curve looks the same coming at it from this side as from the back, as from the right, as right. I should say every point on the curve looks the same coming at it from every direction. So there isn't really a good sense of what counts as across for a curve. So we aren't going to be able to calculate flux integrals for a curve in 3 space, just because that doesn't really make any sense. But what we can do is imagine the flux of a vector field across a surface. So if we have, say, imagine sort of having some sort of circular membrane stretched around a loop like this, we could ask for every point on this surface, how much does each vector point in the vector field point across that surface? So to talk about flux integrals in 3 space, we need to be able to work with surfaces. But we haven't actually worked with surfaces very much in 3 space, so actually we need to back up a step. And before we talk about flux integrals in 3D, first we need to talk about surfaces. So the idea here is what we're going to do is imagine that we have sort of a flat sheet of material, and this is going to be living usually in the UV plane, so some parameter space. And we're going to imagine sort of doing some sort of operation on it to situate this sheet of material in 3D space. And along the way, it's probably going to get bent around and twisted to make the shape of the surface that we want. But that's okay, because it's not a physical sheet of material, so we can bend it. Right, so the idea here is if you imagine sort of a coordinate grid in the UV plane, right, that the corresponding coordinate grid is showing up on the graph here. So, right, every point over here on the UV plane corresponds to some point over here on the surface, right? Maybe this point corresponds to that one. Maybe this point corresponds to that one, right? So what are we going to have to do? What sort of information are we going to have to supply to determine how this sheet of material is getting positioned in XYZ space? Well, what we're going to have to do is for every value of u and v, at least every value in some given region in the UV plane, what we're going to have to do is say what is the corresponding x coordinate, y coordinate, and z coordinate in 3D space, right? Well, different u's and v's are going to give us different x, y's, and z's. So really, x, y, and z are all functions of u and v. And now what it looks like, so what we have to do is write down 3 scalar valued functions, all of which are functions of both u and v. Okay, so when we do this, right, the usual way that we would package up this kind of information is to write it as a vector valued function. And then we can just imagine that the vector that this produces is always a position vector. Okay, so this, along with, this information, 3 scalar valued functions that tell you x, y, and z, all packaged up into a vector valued function that we'll call r. along with some region in the UV plane in your parameter space. This is how we will describe surfaces in 3D space. So the usual term for this is a parametric surface. So given some vector valued function and some domain in the UV plane, then all the image of that region in the UV plane is called a parametric surface, and the vector valued function itself is called a parametrization of the surface. So an image is, by the way, an image is just the collection of points that you get by putting all of the points in D into the function R. So the image is just everything that comes out of your parametrization. I am being a little careful to distinguish between the collection of points that you get, which is the parametric surface, from the function that we are using to trace out this parametric surface. That's R, that's the parametrization. And the reason that I'm being a little careful about that is because, of course, one surface can have many different parametrizations. We'll see common examples of parametrizations in a minute, but you'll see there are always variations that you could, for any given parametric surface, there are always variations you could make on the parametrization that would change the function R, but would not change the collection of points that are covered by the parametric surface. So usually when we ask questions about a parametric surface, at first, we aren't necessarily interested in any particular parametrization. We're interested in the geometric object that is the collection of points itself, the parametric surface. But how we answer questions about parametric surfaces, how we do calculations involving parametric surfaces, will usually involve writing down a parametrization and then using the parametrization to do some kind of calculation.